All right, class, settle down. Now, I know everybody had a fun spring break, but we got to get right down to business today. We're starting a new topic, binomial theorem.
Yeah, math!
Now, I know this might seem a little intimidating, new topic coming in, but it's okay. It's based off of things we've already learned together in class here. For instance, who here can remind us what a binomial is? Kaylee?
Two-term polynomial.
Yep, two-term polynomial, so just an expression that we've created here. So I'm going to go ahead and write up the binomial theorem formula here on the board for you. But while I'm doing that, I want you to pay attention to what I've got over here on the left board. I got a little game here. It's a little pattern. It starts off with 1, breaks off into 2 1s, breaks off into 1 2 1. Some of you may have seen this pattern, some of you may not. But humor me here and try to complete the next couple lines of this pattern following, and I'll go ahead and write the formula on the board. Alright, time's up. So the formula's up there. A little intimidating, I know. But there's a lot of pieces there that we're going to break down. But before we do that, I want to go over here to our game. Did anyone actually recognize this pattern? Shelby.
Yeah, Pascal's triangle.
It is Pascal's triangle. So Shelby, what would be the next line of Pascal's triangle?
That's 1.
Okay.
3.
Okay.
3.
Okay.
1.
Alright. And now, does anyone remember how we get those new rows following this pattern? Maybe if you're not familiar with Pascal's triangle. Donna.
The 2 numbers above add to the same number below with 1 along the sides.
Yeah, can you all see that? So the numbers that are just above each number, in this case the 3, it's the sum of the 1 and the 2 above it. Same here as this 2 is the sum of the 2 1s above it. And then all along the sides here we've got 1. So following that same pattern, what will be the next line on this? Claire.
1.
1.
4.
Okay.
6.
Absolutely.
4.
Yep.
1.
You got it. Okay, so this is a pretty basic pattern. You can do this at anytime you want. It's a fun little thing. But we're going to see how it applies to our binomial theorem formula. And to do that, we're going to have to do a few expansions to start out. So I'm going to do a real basic one here. We'll do a plus b squared. And as we learned, all of our exponents here just show that that binomial or that term are going to be multiplied by themselves a number of times. In this case, twice. Alright, now who can tell me the final expanded form of this binomial after we performed a FOIL? Christine, you got your hand raised?
Yeah, a squared plus 2ab plus b squared.
Very nice, very nice. Okay, so now let's take this one here. I'm going to put a little box around it. And now let's go ahead and multiply that by one more. So in this case, now we're looking at a plus b cubed, because we're going to be multiplying by another one of those binomials. So now who can tell me what this expands out to? Donna.
For the cubed,
For the cubed.
a cubed plus 3a squared b plus 3ab squared plus b cubed.
Very nice. Okay, another box. And then I want us to do that one more time. I'm going to go ahead and add one more binomial. Now we're dealing with our a plus b to the 4th power. Kaylee, why don't you go ahead and expand this one for us?
Okay, a to the 4th
A to the 4th, okay.
plus 4a cubed b
Okay.
plus 6a squared b squared plus 4ab cubed plus 4b to the fourth.
Outstanding. All right, so I want us to just focus on the results here with our fully expanded form. So I'm going to erase all the distractions from around our fully expanded forms. Now, who here can point out any observable patterns we're seeing as we go across our expansions? It can be anything at all. Claire, do you notice anything?
The b exponents increase by 1.
They do.
And
Every single time we go down a term, we either add a b or the power of b goes up by 1. And that's consistent throughout each one of our lines here. Anything else?
the a exponent decreases by 1.
These a exponents. Hey, come on now! No phones in class. So yes, the a exponents are decreasing by 1, or in the case of the last term, it's not even there at all. It's dropping away. That's because the exponent is dropping to 0, making that term become a 1, being multiplied. And that, again, is consistent throughout each of our patterns. Now there's one more thing that we're looking for here. Kaylee, did you spot it?
The coefficients match the triangle.
They do match Pascal's triangle. Look at this. We've got a 1, because there's no coefficient here, so we're going to assume it's a 1. We've got 1, 2, 1. Well, hey, that's a line that was from Pascal's triangle. And then our next line down, 1, 3, 3, 1. Matches up again. And surely, wouldn't you know it, 1, 4, 6, 4, 1. They all match. All the coefficients of our terms of our expanded forms match up exactly to that of Pascal's triangle.
Darn, Claire, I didn't notice that.
And so this is the key thing I wanted you all to notice today. So, I'm going to give you a little homework. Page 298, problems 1 through 6. These are going to just go over a few expansions. Make sure that you remember all the steps that we need to take in that. And then next class, we're going to actually see how each part of this binomial theorem formula actually accounts for each of those patterns. So that way, if we're using the formula, we can accurately predict what those fully expanded forms are going to look like. All right, class dismissed.